Do you know how to speak binary? Yeah, most people don't. So it puts us in a bit of a problem here. We've got a pretty good LED lighting circuit so far, but in order to make sense of the intensity level without actually seeing the intensity, you gotta be able to speak binary, which isn't really gonna take us very far. Take a look. We put in a rotary encoder into this mix here. So using this rotary encoder, I can actually increase the intensity by spinning it clockwise and by decreasing the intensity by spinning it counterclockwise. If you're interested into the details as to how we got this rotary encoder to work in here, make sure you look at the last episode. I'll put a link in the description so you can see it. By increasing the intensity, we're able to get it all the way to the maximum. And if we keep spinning it, nothing happens. And if I bring it down, we can bring it to minimum. Of course, keep spinning, nothing happens. You saw the LEDs, the high power LEDs light up and then go back to zero. But there's also these indicators here. So if I kind of move this spaghetti of wires away so you can see it better, as I increase the intensity, you see those blue indicator LEDs down there? They're changing the pattern. And so the zero pattern, or it's the lowest intensity, is like this. And as I start increasing it, the pattern changes so that eventually it gets to the maximum intensity and all of the 5 LEDs are on. Well, that pattern is binary. And so it's not all that user-friendly because, you know, like I said, most people don't know how to interpret binary. So you can't quite tell that, hey, this is 0 and this pattern is actually, oh, not that one. This pattern is the halfway pattern. So that's 50%. Now, you wouldn't know that unless you can actually speak binary. So we got to make this a little bit better. What I'd like to do is take that 5-bit binary code and decode it into, I don't know, let's say 32 individual indicator lights. And those 32 individual indicator lights will light up so that, you know, all the way at one side will be minimum. And as we start increasing the intensity, at some point it'll get to the middle and right to the end. So it'll function the way you expect it to function. But in order to do that, we're going to have to implement these things called decoders. To better understand binary decoding logic, let's take a look at the codes and see what they need to turn out to. So what I've got here is I've got the first intensity level 0. So this is off, all lights off. The 5-bit code that represents that intensity is, well, as you might expect, all 5 zeros or 5 off. But the indicator level that we want to see is we want to see a light on at the lowest possible indicator. And we got all these other zeros here to represent off LEDs or off lights because it's not, well, the intensity is at the lowest point, right? So as we increase the intensity, I expect to see that 1 or that indicator move up the scale, and the maximum intensity, I'd like to see it right at the end over here saying this is a 1. So this is the first code, 5-bit code, and I need to decode it into this 32-bit code. The next code looks like this. It looks exactly the way you expect it. But the indicator level, I want that light to move up 1 notch. The next one looks like this. So that's where things start getting a little bit unexpected, right? Unless you know binary, you wouldn't know that this pattern equals 2. It does, for those of us who do know binary. But again, I want that to look like this on my indicator. Let me fill in the rest here just for clarity. Let's keep going with this. That was painful. I have computers everywhere around me, and yet, like a crazy person, I insist on using pencil and paper. What's the matter with me? So, Can we do this? Can we take or can we buy on the market a decoder chip? Well, sure you can. But finding a decoder to do this is probably going to be a difficult task. I mean, look at what we have here. We have at least 5 inputs, right? 5 inputs for these 5-bit codes. And we're going to have at least 32 outputs. So that's 5 plus 32, that's 37. The chip is also going to have a 1 power and 1 ground. So it's 39. This is a 40-pin monster, if it even exists. I don't think I've ever seen one. So we can't quite get this in its entirety. We're going to have to build this out of other components. So can we get a 4-bit decoder, 4 to 16-bit decoder? Perhaps we can use 2 4 to 16-bit decoders to build this. I think so. I think I've seen a 4 to 16-bit decoder, but that's also a pretty mighty chip, right? 4 pins in, 16 pins out, plus the power and ground. It's a 22, at least 22, 24 pin chip. That's also quite large. So I don't know that I'd want to get that. Now, a 3 to 8 decoder, so 3-bit to 8 output, we can probably use 4 of those to make this work. And those do exist. There is a 3 to 8 decoder. That's quite common out there. And I have a couple, but what I have is I have a couple of 3 to 8 decoders, but they're a different logic family. See, so far, all of the chips that we've been using on our LED driver circuit, I've deliberately used the 4000 series logic chips. And the reason I've used that is because we're running 12 volt LEDs. And rather than trying to have multiple power supplies, I'd like to run my chips off the same power supply. So I need to have logic chips that work on 12 volts. And these 4000 series logic chips, they'll work up to 18 volts. So really it was out of the spirit of laziness that I decided to use the 4000 series logic chips. Now, in the 4000 series logic chips, I was unable to find a 3 to 8 decoder, but I was able to find a 2 to 4 decoder. We're going to need a few of those, but we have them. So here's what we're going to do. We're going to take this 32-bit monstrosity output, and we're going to basically package it up into small chunks, and we're going to assemble those chunks together so that we can eventually end up with this. We're going to start small and build our way up. So rather than having 32 pins, I'm going to have 4 LEDs that show the indicator level. I could take this and carve it up into blocks. I can define 4 blocks out of these. And if I define 4 blocks, that will be, well, from 0 to 7, 8 to 15, and the other 2 that you can't see, I haven't written those down. But from blocks 0 to 7, these 2 bits do not change. Bit number 4 and bit number 3, so if this is 0, 1, 2, 3, 4, 3 and 4 do not change. You can see how they're all 0, 0. And then the next block, I have 1 and 0. So these 2 never change. And then the next block, if you could see it, would actually have a 1 and 0 this, or 0 and 1 this way, which wouldn't change. And the final block would be 1, 1. So those are 4 different combinations of the most significant bits of this 5-bit code. And each one of those combinations covers 8 intensity levels. So what I can do is I can carve it up that way, and what we result in is this. Here are those 4 combinations. You can see how the lower 3 bits I've kind of crossed out. I'm not interested in them. I don't care what they are. I only care about these 2 bits. And those 2 bits will give us indicators that look like this. So for the first combination, 0, 0, I'll get an indicator level that looks like this, 1, 0, 0, 0. And this will persist for the first 8 intensity levels. That's okay. The next 8 intensity levels, I'm going to get this code, and the indicator level that I want should look like this. See? And then the next one will look like this. Then finally, this is what we want out of an output. And here's what we have for an input. 2 bits in, 4 bits out. And we can use this magnificent chip right here to do that. This is a 4555 or 4555, I don't know, depending on how you want to say it, 4555 chip. Now, this chip in particular actually has 2 of these decoders built in. I'm going to wire it up like this. I'm going to take our lower of the 2 bits. So what I mean by lower, I mean the lower significance of those 2 bits. In that case, that's going to be bit number 3. So this one right here. And I'm going to wire that up to input A on the chip. And the higher significant bit, this one, I'm going to wire that up to input B on the chip. The outputs, Q1 through Q3, I'll just wire directly up to our indicator LEDs. Now there's one other pin on this chip that we haven't quite covered in this diagram, and you'll see it on the next iteration. For now, let's build this and see what happens. All right, I said we'll build it, but I actually kind of put the chips in place. So the first thing you're noticing is that we got a lot more space. I actually had to bring in 2 more breadboards because, well, although we have a little bit of space here from our last circuit, so here's our rotary encoder and here's our the rest of our LED driver circuit. The actual LEDs, the high-powered LEDs, are off the screen. You can't see them right now, but this little space that I had here, it wasn't enough. I mean, first of all, we have 32 indicators that we need to put in, so there's not enough space here for 32 LEDs, so I had to bring in another board entirely so I can put those 32 in. And you can see that 4 of them are here. They're in the corner over there. And so I have these 4. But I also need room for the chips because we're using 2 to 4 decoders and we're going to need a bunch of them. So I needed to bring in 2 more breadboards. So this is going to make our circuit a lot more messy than it already is. And look at this monstrosity. So I promise I will clean this up. I said that before. In fact, I don't want to keep unfinished promises or not keep my promises. So I will clean this up, just not today. In a very, very near episode, maybe even the next one, I'll clean this up. For now, let's just keep going. Okay, so I said we'll build it. So here's the 4555 chip that's already been placed in the breadboard. The only thing that I've connected is I've connected the power, ground, and a couple of other leads here that are going to help ground our system. This happens to be that mystery pin that I haven't quite yet told you about. I'll tell you about in a little bit. But what I need to do is I need to connect my 2 inputs and my 4 outputs. The 2 inputs are going to come from bit 3 and bit 4 from our constant current driver circuit, and the 4 outputs are going to go to these 4 LEDs that I have here. Let's wire it up. I can appreciate that the LEDs are really tough to see. They're tucked away deep in the lower right-hand corner of the screen. So just my apologies. We're going to fill the screen later on. But for now, just take a look at those. And right now we're at minimum intensity. LEDs are off, and we can see the lowest indicator is lit. As I increase it, you'll see the intensity start to rise, and my indicator starts to go up. And you can see the bit pattern and the resulting indication. There it is. There's at the maximum. So this serves as a 4-bit indicator for our LED lights. Now that's nice. Let's scale it up. Let's add another one and make this, instead of 4, let's make it 8. So if we're going to do 8, we're actually taking a 3-bit input and we're turning it to an 8-bit output. So this is a 3 to 8 decoder. But remember, we're going to use 2 of the 4555 decoders that we have so that we can combine them to make a 3 to 8-bit decoder. And this is how we're going to do it. So here's our 5-bit code. See how I'm now looking at 3 of the bits, and the indicator level is going to look like this with 8 possible zones or 8 possible lights. Now we're going to use the whole 455 chip because remember I said each one of these chips actually has 2 decoders in it. So we can see the AB input and they're connected. Both AB inputs are connected to bit 3 and 4 this time, or my mistake, 2 and 3 this time. We're not looking at 3 and 4. We're looking at these 2 bits because they're the least significant bits. The most significant bit is connected to that other mystery input. So what this other mystery input is, it's an enable input, and it's really important because if we don't use the enable input and we try to use these 2 bits to connect to A and B, what we're going to get is we're going to get the same pattern we just got, but we're going to get it 4 times, right? Or twice actually. So at the lowest level of intensity, we're going to have this one on and this one on, and they're going to kind of both move up at the same time. But what we need to do is we actually have these 4-bit blocks, and we need to either enable the block or disable the block, and that's what this enable pin is for. So for example, take a look at the first block, or the first 4 bits. The first 4 bits, bit number 4, the most significant bit, is 0. And if that bit is 0, then what that means is this 0 feeds into this enable. And notice a little line on top of that E? Well, that little line means it's inverted. So a 0 means that this is enabled. And if that's true, then the first 4 bits, this part of our 4555 is going to be enabled. So these Q outputs are on. So that means that as we go through these codes, 0, 1, 2, 3, these 4 indicators or these 4 positions will be lit. The moment we get to the next code, this code represents a 4 in binary logic, but the most significant bit has turned into a 1. And when that turns into a 1, that disables this output. So regardless as to what the A and B inputs are, you'll always get 0 out on this output. And that's what we expect to see. But when this turns into a 1, there's this little inverter here. That's what this function is. And this inverts this 1 to a 0. So this bottom half of that 4555 becomes enabled. And we start to see that same pattern emerge, 0, 1, 2, 3, on the right half of the indicator level. So we get this pattern. Together, it should give us exactly what we want. So the only difference here, of course, we got to wire up the rest of these lines, but the only difference is this inverter. We can use any inverter. And in fact, in the previous episode, when we were implementing our rotary encoder, we did make use of an inverter. And I actually do have it on the board, and there's a bunch of inverter slots available. So I could use it. But rather than doing that, we only need one. And as you're going to see in perhaps the next video, when I start to clean this up, I want to try to modularize these components. What that means is I don't necessarily want wires coming back to another module, like in this case, it would be the rotary encoder. I don't want a wire coming back to the rotary encoder and then going back out to the decoders again. So I want to try to keep this simple, is basically what I'm saying. In order to keep it simple, I'd like to either put in an inverter chip, which might seem like a bit overkill because an inverter chip has 6 inverters and I only need 1. But I can also use a MOSFET, just a regular plain old MOSFET to do that inversion. And that's what I'm going to do over here. If you're interested to see how to wire up a MOSFET to do an inverter, it looks like this. If I do this, this will effectively invert that signal and get me the inverter that I want. Let's wire it up. And there you have it. A 3 to 8-bit decoder. Working as expected. Let's scale it up more. So to get to the next level, we're actually going to have to use 4, or actually I should say the 2 4555 chips. But there, of course, are 4 blocks in here. And of course, we've expanded the 5-bit code to include D1 and D2. We're still ignoring D0. We'll get there next. But right now we're looking at D1 and D2. And so D1 is connected to all of the A inputs for all of these chips. D2 is connected to all of the B inputs for all of the chips. That's the same. That hasn't changed. But in order to make these enables work, we actually have 4 different possibilities. So I can't use a simple inverter because an inverter only gives us 2 possibilities. But remember, we have these decoder chips, so I can actually use the other 2 bits and feed them into yet another decoder, which will in order go from E1, E2, E3, E4. So it'll actually turn each one of these zones on in order depending on the combination of D3 and D4. So this will work really good, but there's one slight difference. If you remember, these these enable pins are actually inverted. They have that line on top of them, which means that it will be enabled when it receives a 0, not when it receives a 1. And these 4555 chips, they output a 1. So if I wire this up this way and use a 4555 chip over here, what I'm actually going to get is I'm going to actually get all of the other blocks that need to be off. They're going to be on, and the one that I want to be on is going to be off. It's actually going to give me the inverted result. So I can fix it. I can fix it if I put an inverter in between all of these outputs. So basically, whatever output comes out of this chip, I'm going to invert it, and that will give me the result that I want. So I could do that, but I got to use 4 inverters, 4 MOSFETs, or get another chip. There's an easier way. There is another chip out there, actually called the 4556. It looks just like the 4555. It does the exact same thing with the one exception that it inverts the output, and that will give the results that we want. So let's wire this up and see where it takes us. Am I back? Yeah, I think I'm back. All right, so I'm experiencing equipment failure and my camera failed while I was wiring it up. So unfortunately, I couldn't show you the remainder of the wiring. The next step is to take it to a full 32 or a 5 to 32-bit decoder. So right now we have a 4 to 16 and we're using we're actually using two 4555 chips and half of a 4556 chip. So we're going to have to double that. So we're going to need four 4555 chips, and I don't have to add another 4556 chip because I'm only using half of it. I'm going to have to end up using the other half. But this is going to get huge. I mean, I'm going to have a big bowl of spaghetti wire, bowl of spaghetti mess of wires on these breadboards, and then you're going to see why I really needed to add two more breadboards. But let me just do that, and because of my equipment failure, I'll come back when it's all done. You'll see me in a sec. Look it's beautiful, and it works. Watch as I turn the encoder here and increase the intensity of my LEDs. Look at that indicator. It's so wonderful. It just nicely glides from the top to the bottom, from the bottom to the top. And it works just as expected. 32 different intensities corresponding to 32 different positions on that indicator dial. Do we really need 32? I mean, I don't know, it verges on the impractical, right? I mean, look at what we needed to do to make that happen. We have all of these wires, 32 different LEDs, 4 breadboards, and 5 new chips just to get an indicator. It's a lot. Is it practical? It was definitely fun to build, though, that's for sure. So I don't know about practicality. I think if we're interested in building it just for academic sake, yeah, I mean, that was great. But if we're going to make this into a practical, a practical lighting application, I mean, that's going to take up a lot of board space. So I don't know if we actually want to do that. If we just cut it down by half, so rather than 32 lights, we can make it 16. That is still very functional, right? And we'll still be able to show the indication of the level of the intensity. But it will take up half the amount of circuitry that we have here. It'll only require 3 of these chips, the amount of wires we cut down by half, and it'll take up a lot less board space. So I think practicality-wise, I might be tempted to go with 16. Anyways, that aside, I think what we've done here is pretty cool. It's pretty profound, right? We've actually gone and created this giant mess, and we've built a really cool lighting system. But it's time to fulfill my promise, or at least promise that I'm going to fulfill my promise, right? I've promised before that I'm going to clean this mess up. It is a terrible mess of wires. And what I was thinking originally was I was going to take this mess of wires and start soldering it onto prototype boards. Now, I thought about that again, and I'm like, that's just going to add a few more steps. I think I want to skip a step. I'm going to skip the prototype board and go straight to custom printed PCBs, or custom printed circuit boards. Oh, that's going to be fun. See you then.